Tonight, we're going to embark on a journey that spans 4.6 billion years of cosmic history. We're going to witness the birth of everything we call home. From the sun that warms your face to the ground beneath your feet. This isn't just astronomy. This is the story of how atoms scattered across cold, dark space came together to build worlds, moons, and eventually life itself. By the end of this exploration, you'll understand the astonishing processes that transformed a drifting cloud of gas and dust into the intricate clockwork of planets, asteroids, and comets that we know as our solar system. Before we begin, if you find yourself drawn into this cosmic journey and want to explore more mysteries of the universe, consider liking and subscribing to the channel. Now let's turn back the clock to a time before there was any clock at all, before there was a sun to mark the days, before there was an Earth to call home. The question of how our solar system formed has captivated human minds for centuries. Ancient civilizations looked up at the wandering planets and wondered about their origins. The Babylonians tracked their movements with meticulous precision. The Greeks gave them names and wove them into their mythology. But it wasn't until the age of scientific inquiry that we began to piece together the true story of our cosmic origins. In 1734, a Swedish scientist named Emanuel Swedenborg first proposed that the planets might have formed from material surrounding the young sun. This idea was refined and expanded by the German philosopher Immanuel Kant in 1755, and later by the French mathematician Pierre-Simon Laplace in 1796. Their nebular hypotheses suggested that the solar system emerged from a rotating cloud of gas and dust that gradually condensed and formed the sun and planets we observe today. Though their original ideas required significant refinement, the core concept has stood the test of time and remains the foundation of our modern understanding. The E scale of what we're about to explore defies easy comprehension. Our solar system spans approximately 287 billion kilometers from the sun to its outer boundary at the heliopause. If you could travel at the speed of light, the fastest possible speed in the universe, at roughly 300,000 kilometers per second, it would still take you about 18 hours to traverse from one side to the other. The objects within this vast space range from dust particles smaller than a grain of sand to the sun itself, which contains 99.86% of all the mass in the solar system. Everything else, all 8 planets, all their moons, all the asteroids and comets, together make up less than 0.25% of the solar system's total mass. And yet, despite this overwhelming dominance of the sun, the story of our solar system is largely the story of how that tiny remaining fractions organized itself into worlds. Some of these worlds are barren rocks baked by the sun's radiation. Others are frozen ice balls, drifting in perpetual darkness at the outer reaches. One of them, remarkably, developed conditions suitable for life, and on its surface, beings evolved who could look up at the stars and ask how it all began. Let us begin at the very beginning, before there was a sun, before there were planets, before there was anything we would recognize as our solar system. We must travel back 4.6 billion years to a time when this corner of the Milky Way galaxy was occupied by something far less impressive than the solar system we know today. It was occupied by a cloud. Part 1, the birth of our star. Picture an immense cloud of gas and dust drifting through the galaxy. This is a giant molecular cloud, one of the coldest and darkest places in the universe. These cosmic nurseries can span hundreds of light years across and contain enough material to form thousands of stars. The one that would become our solar system was likely just a small fragment of a much larger structure, perhaps similar to the famous Orion Nebula that we can observe today with modest telescopes. Within this primordial cloud, the gas was predominantly hydrogen, the simplest and most abundant element in the universe. Helium, the second lightest element, made up most of the remainder. Together, these two elements accounted for roughly 98% of the cloud's mass. The remaining 2% consisted of heavier elements that astronomers somewhat imprecisely call metals, a term that in this context refers to anything heavier than helium. This small fraction included oxygen, carbon, nitrogen, silicon, iron, and traces of every other naturally occurring element. These heavier elements are crucial to our story. Hydrogen and helium were forged in the Big Bang itself, created in the first few minutes after the universe began approximately 13.8 billion years ago. But heavier elements require different conditions for their creation. They can only form in the cores of massive stars, where temperatures and pressures are extreme enough to fuse lighter elements together. When these massive stars die, they explode as supernovae, scattering their enriched material across space. The cloud that would become our solar system was seeded with the remains of countless dead stars, generations of cosmic furnaces that had lived and died over billions of years before our sun was born. For millions of years, perhaps longer, this cloud drifted peacefully through the galaxy. The gas within it was so cold, only about 10 to 20 degrees above absolute zero, that molecules moved sluggishly, rarely colliding with enough energy to do anything interesting. The cloud was stable, held up against its own gravity by the thermal pressure of its gas, by turbulent motions within, and by magnetic fields threading through it. Something would need to disturb this equilibrium to set the stage for solar system formation. That something, according to one leading hypothesis, was a supernova. Research led by Professor Yongjong Qian at the University of Minnesota has provided evidence that a dying star, one with roughly 12 times the mass of our Sun, may have exploded in the vicinity of our nascent solar nebula approximately 4.6 billion years ago. The evidence for this possibility comes from an unlikely source: ancient meteorites that have fallen to Earth. Meteorites are the remnants of the solar system's earliest days, fragments of asteroids and other small bodies that have survived largely unchanged for billions of years. They are, in essence, time capsules from the birth of the solar system. When scientists analyze these space rocks, they find traces of short-lived radioactive isotopes that were present when the solar system formed. The origin of these isotopes remains an active area of scientific debate. One particularly studied isotope is beryllium-10. This unstable form of beryllium has a half-life of only 1.387 million years, meaning that half of any sample decays within that time. For beryllium-10 to be present in meteorites that formed 4.6 billion years ago, it must have been freshly synthesized and quickly incorporated into the materials from which those meteorites formed. Qian and his colleagues proposed that beryllium-10 could be produced by neutrino interactions during supernova explosions. However, more recent research has challenged this interpretation. Studies published in 2024 by scientists at Oak Ridge National Laboratory suggest that reaction rates within supernovae would actually destroy beryllium-10 faster than previously thought, leading some researchers to conclude that cosmic ray spallation, rather than supernovae, may be the primary source of this isotope. The debate continues, illustrating how our understanding of these ancient events continues to evolve. Other isotopes provide additional clues, though their origins are similarly debated. Calcium-41, with a half-life of about 100,000 years, and aluminum-26, with a half-life of approximately 717,000 years, have both been detected in meteorites. For decades, scientists assumed these isotopes came from a nearby supernova or massive stellar winds. However, recent research has proposed that the young sun itself could have produced aluminum-26 through cosmic rays generated during the violent accretion process. The presence of iron-60, which decays into nickel-60 with a half-life of 2.6 million years, is more difficult to explain without external stellar input, suggesting that at least some material from dying stars did contribute to our solar system's formation. These isotopic fingerprints are the forensic evidence that helps us reconstruct what triggered our solar system's birth, even as the full picture continues to come into focus. When the supernova exploded, it sent a shockwave racing through space at thousands of kilometers per second. This expanding shell of hot, fast-moving gas eventually encountered the cold molecular cloud that would become our solar nebula. This collision was gentle by cosmic standards, but it was enough to compress regions of the cloud, increasing their density and triggering gravitational collapse. Once gravity took hold, the process became self-reinforcing. As the cloud fragment contracted, its density increased, strengthening its gravitational pull. This drew in more material, which further increased the density, which further strengthened gravity. The collapse accelerated, and within perhaps 100,000 years, what had been a diffuse wisp of gas and dust began to resemble something more organized. As the cloud collapsed, it spun faster and faster like an ice skater drawing in their arms. This is a consequence of the conservation of angular momentum, one of the fundamental laws of physics. The cloud's original rotation, however slight, became amplified as its radius decreased. This increasing rotation rate had a profound effect on the cloud's shape. Material could fall freely toward the center along the rotation axis, but in the equatorial plane, centrifugal force resisted the inward fall. The result was a flattening of the cloud into a disk shape, with material accumulating in a plane perpendicular to the rotation axis. At the center of this collapsing rotating mass, pressure and temperature began to climb. As material piled on, the weight of the overlying layers compressed the core, converting gravitational potential energy into heat. Within a few 100,000 years, the core had grown hot enough to glow, first in infrared radiation, then in visible light. This was the protostar, the embryonic sun, not yet massive enough or hot enough to ignite nuclear fusion, but already the dominant object in its nascent system. The protostar continued to grow as material from the surrounding disk spiraled inward and fell onto its surface. This process, called accretion, is turbulent and episodic. The young star would occasionally flare in brightness as clumps of material crashed onto its surface. These outbursts, which astronomers have observed in young stars throughout the galaxy, can temporarily increase a protostar's luminosity by a factor of 100 or more. Surrounding the growing protostar was the solar nebula, a disk of gas and dust that would eventually give birth to all the planets, moons, asteroids, and comets we observe today. This protoplanetary disk extended outward for hundreds of astronomical units, where one astronomical unit is defined as the average distance from Earth to the Sun, about 150 million kilometers. The disk was not uniform in composition or temperature. Near the protostar, where temperatures could exceed 2000 degrees Kelvin, only the most refractory materials could exist as solids. Further out, where temperatures dropped below the freezing point of water and other volatile compounds, a much wider variety of solid materials could persist. After about 100,000 years of rapid growth, the protostar had accumulated most of the mass it would ever have. Its core temperature had climbed to roughly 10 million degrees Kelvin, and at this temperature, hydrogen nuclei began to fuse together, forming helium and releasing enormous amounts of energy. The sun had ignited. Nuclear fusion would power our star for the next 10 billion years or more, providing a stable source of warmth for any planets that might form around it. The ignition of fusion marked a turning point in the solar system's early history. The newborn sun began to emit powerful stellar winds, streams of charged particles that swept outward through the solar nebula. These winds, combined with the sun's intense ultraviolet radiation, began to erode the gas in the disk, gradually dispersing it back into interstellar space. The clock was now ticking on planet formation. Any worlds that would emerge from this disk would need to form within the next few million years before the raw materials were swept away. Part 2. The protoplanetary disk. The protoplanetary disk surrounding our young sun was a dynamic, complex environment where the seeds of planets would be sown. To understand how worlds formed from this disk, we must first appreciate its structure, composition, and the physical processes that operated within it. The disk was primarily composed of gas, with hydrogen and helium dominating by mass. However, the solids, though representing only about 1% of the total mass, would prove crucial for planet formation. These solids existed initially as microscopic dust grains, each one typically less than a micrometer in diameter. These grains were not simple, uniform particles. They included silicates, which are rocky compounds of silicon and oxygen. They included metallic grains of iron and nickel. And further from the sun, where temperatures were low enough, they included ices of water, carbon dioxide, ammonia, and methane. The temperature gradient across the disk determined which materials could exist as solids at any given distance from the sun. Close to the protostar, within about half an astronomical unit, temperatures exceeded 1,500 degrees Kelvin. At these temperatures, even the most heat-resistant minerals were near their melting points. Only refractory compounds like aluminum oxide and calcium titanium oxide could condense as solids in this innermost region. Moving outward, the temperature dropped steadily. At around 1 astronomical unit, roughly where Earth would eventually form, temperatures were perhaps 300 to 400 degrees Kelvin. Here, silicate minerals could condense readily, as could metallic iron and nickel, but water, carbon dioxide, and other volatile compounds remained in gaseous form, unable to contribute to the formation of solid bodies. The location where water ice could first condense as a solid is called the frost line, or sometimes the snow line or ice line. In our solar system, this boundary was located at approximately 2.7 astronomical units from the Sun, roughly corresponding to the middle of what is now the asteroid belt. Evidence for this location comes from observations of asteroids. Those in the inner asteroid belt are predominantly rocky S-type asteroids, similar in composition to the silicate-rich meteorites called ordinary chondrites. Those in the outer asteroid belt are dominated by dark C-type asteroids, which contain significant amounts of water and carbonaceous compounds. The dwarf planet Ceres, the largest object in the asteroid belt, with a diameter of about 940 kilometers, orbits at a distance of 2.77 astronomical units, almost exactly at the estimated position of the frost line. Ceres appears to have an icy mantle beneath its rocky crust and may even possess a subsurface ocean of liquid water. Its position and composition make it a marker for where water ice first became available as a building material in the early solar system. Beyond the frost line, the abundance of solid material increased dramatically. The condensation of water ice added a substantial component to the mix of solid particles available for planet formation. Calculations suggest that the surface density of solids beyond the frost line was 3 to 4 times higher than in the inner disk. This difference would have profound implications for the types of planets that could form in different regions of the solar nebula. The disk was not static. Gas and dust flowed through it, driven by viscous forces that caused material to spiral slowly inward toward the sun, while simultaneously spreading the disk outward at its edges. This process, called viscous accretion, was mediated by turbulence within the disk, though the exact mechanisms generating this turbulence remain an active area of research. One leading candidate is magneto-rotational instability, in which magnetic fields threading through the ionized gas can amplify turbulent motions and facilitate the transport of angular momentum. The dust grains embedded in this turbulent gas were not passive passengers. They interacted with the gas in complex ways, settling toward the disk's midplane under the influence of the sun's gravity, while simultaneously being stirred upward by turbulent eddies. The balance between gravitational settling and turbulent lofting determined the vertical distribution of dust within the disk, concentrating it toward the midplane, where collisions between grains were more frequent. These collisions were the first steps toward planet formation. When two dust grains collided at low velocity, they could stick together through van der Waals forces, the weak attractions between electrically neutral molecules. In the outer disk, where temperatures were cold enough for ices to be present, grains coated with ice mantles could stick even more readily, the ice acting as a kind of glue. Through countless such collisions, dust grains grew into larger aggregates. Fluffy, fractal structures formed first, irregular clumps that could be compacted by further collisions into denser bodies. Laboratory experiments on Earth and microgravity experiments on the International Space Station have demonstrated that this sticking process can efficiently build particles from micrometer sizes up to millimeter and centimeter scales. However, a problem emerges at larger sizes, one that scientists call the meter barrier or the bouncing barrier. As particles grow beyond centimeter scales, their relative velocities during collisions tend to increase, and impacts become more destructive. Instead of sticking, the particles bounce off each other or fragment into smaller pieces. This size range, from roughly centimeter to meter scales, proved difficult to traverse through simple sticking alone. Moreover, particles in this size range face another challenge: rapid inward migration. The gas in the protoplanetary disk orbits the Sun slightly more slowly than a particle of solid matter would orbit in the absence of gas. This is because the gas feels pressure support that partially counteracts gravity, reducing the effective gravitational pull it experiences. Solid particles, which don't feel this pressure support, orbit at Keplerian speeds and thus move faster than the gas around them. They experience a headwind from the gas, which drains their angular momentum and causes them to spiral inward toward the Sun. For meter-sized objects, this inward drift is particularly severe. Calculations suggest that such bodies could spiral into the Sun in as little as 100 to 1,000 years, far too quickly for them to grow into larger planetesimals through gradual accretion. This posed a theoretical puzzle for planet formation models. How could planets form if their building blocks were being destroyed or lost before they could grow to safe sizes? The solution to this puzzle appears to involve collective processes rather than individual particle growth. One influential mechanism is called the streaming instability, first described by Andrew Youdon and Jeremy Goodman in 2005. When the concentration of solid particles in a region of the disk becomes high enough, the particles can collectively resist the headwind from the gas. Instead of drifting inward, these particle clumps maintain their position and can even draw in additional material from their surroundings. As particles concentrate, their collective gravity begins to matter. When the local density of solids exceeds a critical threshold, gravitational collapse can occur, rapidly forming a bound object with a diameter of perhaps 100 kilometers or more. This bypasses the meter barrier entirely, jumping from pebble-sized particles directly to planetesimal-sized bodies in a relatively short time. Evidence for this formation mechanism comes from observations of the Kuiper Belt, the ring of icy bodies beyond Neptune's orbit. Many Kuiper Belt objects exist as binary systems, pairs of roughly equal-sized bodies orbiting their common center of mass. The properties of these binaries, including the distribution of their separations and mass ratios, are consistent with formation through gravitational collapse of particle clouds rather than through gradual accretion. The first planetesimals in our solar system likely formed in this manner within the first few million years after the Sun's birth. These objects, ranging from tens to hundreds of kilometers in diameter, became the building blocks for the larger bodies that would eventually become planets. They were distributed throughout the disk, from the inner regions where rocky materials dominated to the outer regions where ices were abundant. The formation of planetesimals marked the end of the solar system's initial assembly phase and the beginning of a new era of growth through gravitational accretion. From this point forward, gravity would be the dominant force shaping the architecture of our planetary system. Part 3. The Frost Line and the Great Divide. The frost line stands as one of the most consequential boundaries in the history of our solar system. This invisible demarcation, where temperatures first dropped low enough for water ice to condense as a solid, fundamentally shaped the types of planets that could form in different regions of the disk. Understanding its significance helps explain why our solar system has two distinct families of planets: the small, rocky terrestrial worlds of the inner system and the massive gas and ice giants of the outer system. At temperatures above about 150 to 170 degrees Kelvin, water exists only as vapor in the near vacuum conditions of a protoplanetary disk. Below this temperature, water molecules can stick together and form ice crystals. The location where this transition occurs depends on the disk's temperature structure, which in turn depends on the luminosity of the central star, the opacity of the disk material, and the rate at which heat is transported through the disk. In our early solar system, the frost line was located at approximately 2.5 to 3 astronomical units from the Sun. This placed it just beyond the orbit where Mars would eventually form, and within the region that would become the asteroid belt. The significance of this location cannot be overstated. It created a fundamental divide in the composition of solid materials available for planet formation. Inside the frost line, the only solid materials available were rocky silicates and metallic grains. These materials, though important, represented only about 0.4% of the total mass of the solar nebula. The other 99.6%, consisting of hydrogen, helium, and various volatile compounds, remained in gaseous form and could not be directly incorporated into solid bodies through condensation. Beyond the frost line, the condensation of water ice added substantially to the inventory of solid materials. Water molecules are among the most abundant in the universe, and when they could freeze into ice, the surface density of solids in the disk increased by a factor of 3 to 4. This meant that far more material was available to build planetary bodies in the outer disk than in the inner disk. The importance of this enhancement extends beyond just the raw amount of building material. The increased surface density of solids beyond the frost line meant that planetesimals could grow larger and faster in this region. According to planetary formation theory, the isolation mass, which is the maximum mass a body can reach by accreting material from its immediate vicinity, scales with the surface density raised to the power of 1.5. A threefold increase in surface density thus translates to roughly a five-fold increase in isolation mass. Furthermore, the frost line may have acted as a particle trap, concentrating solid material at this boundary. As water vapor drifted outward through the disk from warmer regions, it would freeze upon crossing the frost line, depositing additional ice onto particles already present there. Conversely, ice-bearing particles drifting inward would sublimate as they crossed the frost line, releasing water vapor that would drift back out and recondense. This cycle could significantly enhance the concentration of solids right at the frost line. The presence of the frost line helps explain one of the most fundamental features of our solar system: the arrangement of rocky planets close to the Sun and giant planets further out. In the inner disk, where only rocky and metallic materials could condense, the limited supply of solid material resulted in the formation of relatively small planets. Mercury, Venus, Earth, and Mars, with masses ranging from 0.055 to 1 Earth mass, represent the best that could be achieved with the available building materials. Beyond the frost line, the story was dramatically different. The enhanced supply of solids, now including abundant water ice, allowed planetary cores to grow much larger. When these cores reached a critical mass, Estimated at around 10 Earth masses, they became capable of gravitationally capturing the surrounding gas in a runaway process that led to the formation of gas giant planets like Jupiter and Saturn. The location of the frost line was not static. As the young sun evolved, and as the disk itself changed over time, the frost line moved. In the earliest stages of the solar nebula, when accretion rates were high and the disk was hot, the frost line may have been located at 5 astronomical units or beyond. As the sun settled onto the main sequence and the disk cooled, the frost line likely migrated inward to its eventual position around 2.5 to 3 astronomical units. This migration of the frost line may have left its mark on the asteroid belt. The compositional gradient observed in the asteroid belt, with rocky S-type asteroids predominating in the inner belt and water-rich C-type asteroids in the outer belt, could reflect the position of the frost line at different stages of the solar system's early evolution. Planetesimals that formed early when the frost line was further out would be rocky throughout much of the belt. Those that formed later, after the frost line had migrated inward, would include water ice in regions where earlier formed bodies were dry. Beyond the water frost line, at even greater distances from the sun, other volatile compounds could condense as well. Carbon dioxide ice forms at temperatures below about 70 degrees Kelvin. Methane and carbon monoxide ices require temperatures below about 30 degrees Kelvin. These additional frost lines, located at progressively greater distances from the sun, further enriched the solid material available for planet formation in the outer solar system. The condensation of these more volatile ices is thought to have contributed to the feeding zones of Uranus and Neptune, the solar system's ice giants. Unlike Jupiter and Saturn, which are composed predominantly of hydrogen and helium, Uranus and Neptune contain substantial fractions of water, methane, and ammonia. Their formation beyond the methane and carbon monoxide frost lines allowed them to incorporate these volatile ices, giving them their distinctive compositions. The frost line concept has proven essential not just for understanding our own solar system, but for interpreting observations of planetary systems around other stars as well. Astronomers have discovered thousands of exoplanets, and the distribution of their sizes and orbital distances shows patterns consistent with the influence of frost lines on planet formation. Giant planets tend to be found at greater distances from their stars, beyond where frost lines would be expected, while smaller rocky planets predominate closer in. The Great Divide, created by the frost line, established the fundamental architecture of our solar system within the first few million years of its existence. This boundary, invisible to our eyes, but profound in its consequences, helped determine that we would inhabit a small, rocky planet in the warm inner reaches of our star's domain, rather than a frozen ice world in the cold outer darkness. Part 4. Building worlds from dust. The transformation from microscopic dust grains to kilometer-scale planetesimals is one of the most remarkable processes in the history of our solar system. This growth by a factor of over 1 trillion in size involved multiple physical mechanisms operating in sequence, each handing off to the next as particles grew beyond the range where one process was effective and into the domain where another took over. In the earliest stages, growth occurred through simple sticking. When 2 dust grains collided at sufficiently low velocities, typically less than a few meters per second, they could adhere to each other through van der Waals forces. These weak molecular attractions, arising from temporary fluctuations in electron distributions, were sufficient to bind micrometer-sized grains together when impact velocities were gentle enough. The grains themselves were diverse in composition. Silicate minerals, including olivine and pyroxene, were common throughout the disk. These rocky materials had condensed from the cooling solar nebula at temperatures of roughly 1,400 to 1,800 degrees Kelvin. Iron and nickel metals, which condense at similar temperatures, were also present as separate grains or alloyed with each other. At greater distances from the Sun, where temperatures were lower, these refractory grains were joined by more volatile materials, including water ice, carbon compounds, and organic molecules. Laboratory experiments have demonstrated that the sticking efficiency of dust grains depends strongly on their size, composition, and surface properties. Grains coated with thin layers of organic material or water ice stick more readily than bare silicate grains. The irregular, rough surfaces of natural grains provide more contact area for adhesion than perfectly smooth spheres would. These factors combined to make the initial stages of particle growth relatively efficient. As particles grew, they developed increasingly complex structures. Early aggregates tended to be fluffy and porous, with fractal geometries that gave them surprisingly large cross-sectional areas relative to their mass. These fluffy aggregates were effective at sweeping up additional small particles, but were vulnerable to compaction during higher energy collisions. Over time, impacts compressed these structures into more compact forms, increasing their density and strength. The transition from microscopic grains to millimeter-scale particles occurred relatively quickly, perhaps within the first few thousand years of the disk's existence. At this size, particles are called chondrules in planetary science nomenclature, named after the small, rounded inclusions found in certain types of meteorites. True chondrules are actually thought to have formed through a different process involving localized heating events in the disk, but the term is sometimes used more loosely to refer to any millimeter-scale particle. The existence of genuine chondrules in primitive meteorites provides direct evidence of the conditions in the early solar nebula. These small glassy spheres show evidence of having been heated to melting temperatures above about 1,800 degrees Kelvin, and then cooled rapidly over a period of hours to days. The heat source for chondrule formation remains debated. Possible mechanisms include shock waves passing through the disk, lightning discharges, impacts between planetesimals, and encounters with the young sun's magnetic field. Regardless of their origin, chondrules became major components of the solid material in the inner solar system. In certain types of meteorites called chondrites, chondrules make up 20 to 80% of the rock by volume. These meteorites are considered primitive because they have undergone minimal alteration since their formation 4.6 billion years ago. They represent samples of the original building materials from which the terrestrial planets were constructed. Beyond millimeter scales, particle growth becomes increasingly challenging. The problem is that as particles grow larger, their relative velocities during collisions tend to increase. Smaller particles are more strongly coupled to the gas in the disk and tend to move at similar velocities. Larger particles, which are less affected by gas drag, can have significant relative velocities, especially if they are on different orbits. When collision velocities exceed a few meters per second, impacts between porous aggregates tend to result in bouncing rather than sticking. At even higher velocities, above perhaps 10 meters per second, collisions become destructive, fragmenting the particles rather than growing them. This creates what scientists call the bouncing barrier or fragmentation barrier, a size range from roughly centimeter to meter scales that seems difficult to traverse through simple pairwise collisions. The meter barrier is compounded by the problem of radial drift. Particles in this size range experience particularly strong drag from the slightly slower moving gas in the disk. This drag removes angular momentum from the particles, causing them to spiral inward toward the sun. At the fastest, meter-sized bodies can drift inward at a rate of about 1 astronomical unit per century, meaning they would be lost into the sun within a few hundred years if they couldn't grow to larger sizes quickly enough. For decades, this posed a fundamental problem for planet formation theory. If particles couldn't survive long enough in the critical centimeter to meter size range, how could planets ever form? The solution appears to involve collective effects rather than individual particle growth. The streaming instability mentioned earlier provides a way around the meter barrier. When the concentration of solid particles in a region of the disk becomes high enough, the particles can collectively resist the headwind from the gas. Numerical simulations have shown that under the right conditions, the streaming instability can concentrate particles into dense filaments and clumps that can then undergo gravitational collapse. When a particle cloud collapses under its own gravity, it bypasses the problematic size range entirely. A cloud of pebble-sized particles can collapse directly into a planetesimal with a diameter of 100 kilometers or more in a very short time, perhaps only a few orbital periods. This rapid formation avoids the problems of bouncing, fragmentation, and radial drift that plague gradual growth through pairwise collisions. The planetesimals that form through gravitational collapse have distinctive properties. They tend to be loosely bound, with significant porosity, and can have irregular shapes rather than the spherical forms that larger bodies acquire under the influence of their own gravity. Binary and multiple systems are common, as the collapsing particle cloud often fragments into two or more bodies that end up gravitationally bound to each other. These predictions are consistent with observations of small bodies in the outer solar system. Many Kuiper Belt objects exist as binaries with nearly equal mass components, which is difficult to explain through collisional processes, but arises naturally from gravitational collapse. The asteroid Arrokoth, visited by NASA's New Horizons spacecraft in 2019, has a bilobed shape that suggests it formed from the gentle merger of two separate objects, consistent with formation through gravitational collapse of a particle cloud. Once planetesimals had formed, a new mode of growth became possible: gravitational accretion. Planetesimals with diameters of 100 kilometers or more have enough gravity to significantly enhance their ability to capture material from their surroundings. This enhancement, called gravitational focusing, means that the effective cross-section for collisions is much larger than the physical size of the body would suggest. Gravitational focusing kicks off a phase of runaway growth, in which the largest planetesimals grow faster than smaller ones. The growth rate of a body depends on its cross-section for capturing material, which is enhanced by gravitational focusing and on its velocity relative to the surrounding population of smaller bodies. Larger bodies tend to have lower relative velocities because gravitational interactions with their surroundings dynamically cool them toward circular low-inclination orbits. This combination means that the biggest bodies grow fastest, rapidly pulling ahead of their smaller companions. During runaway growth, a few dominant bodies emerge in each region of the disk, each one sweeping up material from its feeding zone. These dominant bodies, called planetary embryos, eventually reach masses comparable to the Moon or Mars, with diameters of thousands of kilometers. At this point, the growth dynamics change again, entering a phase called oligarchic growth, in which the largest embryos compete with each other on more equal footing. The end result of these processes was a disk populated by dozens of planetary embryos, ranging from lunar to Mars-sized masses, embedded in a sea of smaller planetesimals. These embryos would eventually collide with each other in a final phase of giant impacts, building up the terrestrial planets we know today. But that stage of the story lies ahead. For now, we have traced the remarkable transformation of microscopic dust grains into world-sized bodies, a process that occurred within the first few million years of our solar system's existence. Part 5. The rocky inner worlds. The formation of the terrestrial planets stands as one of the most violent chapters in the history of our solar system. Mercury, Venus, Earth, and Mars emerged from a chaotic dance of collisions between dozens of Moon-to-Mars-sized planetary embryos, a process that took roughly 100 million years to complete. Understanding this process helps us appreciate just how remarkable it is that our world exists at all. By about 3 million years after the Sun's birth, the inner solar system was populated by a swarm of planetary embryos. These objects, each comparable in mass to the Moon or Mars, occupied overlapping orbits in the warm regions inside the frost line. Surrounding them were countless smaller planetesimals, remnants of the earlier stages of accretion that had not yet been incorporated into larger bodies. The embryos were not arranged in a single plane. Their orbits had various inclinations and eccentricities, acquired through gravitational interactions with each other and with the massive protoplanets forming beyond the frost line. These orbital elements meant that embryos on neighboring orbits would periodically cross each other's paths, setting the stage for the giant impacts that would shape the final terrestrial planets. The first few tens of millions of years saw relatively rapid growth as embryos swept up the remaining population of smaller planetesimals. This phase of accretion was dominated by gravitational focusing, which made the largest bodies the most efficient collectors of new material. But as the planetesimal population was depleted, growth slowed, and the embryos increasingly interacted with each other rather than with smaller bodies. Gravitational interactions between embryos drove slow but inexorable changes in their orbits. Perturbations accumulated over millions of years, gradually increasing orbital eccentricities and inclinations. Eventually, orbits began to cross, and the first collisions between embryos occurred. These giant impacts were world-shaping events, releasing enormous amounts of energy and fundamentally transforming the bodies involved. When two Mars-sized embryos collide, at typical velocities of several kilometers per second, the energy released is staggering. A significant fraction of both bodies can be vaporized, creating a temporary cloud of rock vapor that surrounds the impact site. The collision can strip away outer layers, merge the two bodies into one, or if the impact is sufficiently oblique, scatter debris into orbit around the merged body. Each such collision fundamentally altered the mass, composition, and rotation of the resulting object. The terrestrial planets we observe today represent the survivors of this process, the objects that ended up in stable orbits after the collisions had run their course. Each one bears the scars of its violent origins, though billions of years of geological activity have obscured most of the direct evidence. Mercury, the innermost planet, is a peculiar world. With a diameter of only 4,879 kilometers, it is the smallest planet in our solar system, yet it has an unusually large iron core that makes up about 75% of its radius. This core represents a much higher fraction of the planet's interior than in any other terrestrial world. The most likely explanation is that Mercury experienced one or more catastrophic impacts early in its history that stripped away most of its rocky mantle, leaving behind primarily the dense metallic core. Simulations of such mantle-stripping impacts have shown that they are plausible given the conditions of the early inner solar system. A giant impact at just the right angle and velocity could have removed much of Mercury's original silicate mantle, vaporizing it and sending it into space or into orbits where it could be lost from the system. The Mercury we see today may be the remnant core of what was once a substantially larger planet. Venus, our nearest planetary neighbor, is nearly Earth's twin in terms of size and mass, with a diameter of 12,104 kilometers compared to Earth's 12,742 kilometers. Yet Venus differs from Earth in profound ways. Its surface temperature is hot enough to melt lead. Its atmosphere is a crushing blanket of carbon dioxide and sulfuric acid clouds, and it rotates slowly, backward compared to most other planets in the solar system. The origin of Venus's retrograde rotation remains debated. One possibility is that Venus was struck by a large impactor late in its formation that reversed its spin direction. Another possibility is that tidal interactions between Venus's thick atmosphere and the Sun, combined with the solid body tides raised by the Sun in Venus's interior, gradually slowed and reversed the planet's rotation over billions of years. Whatever the cause, Venus's present-day rotation period of 243 Earth days, longer than its orbital period of 225 Earth days, makes it unique among the planets. Earth, our home, is the largest of the terrestrial planets, and the only one known to possess liquid water on its surface and an active biosphere. Earth's formation was completed by a series of giant impacts, the last and largest of which created our moon and finalized our planet's composition and rotation. Before the moon-forming impact, Earth had already grown to perhaps 90% of its present mass through the accretion of embryos and planetesimals. Its interior had differentiated, with dense iron and nickel sinking to form a metallic core, while lighter silicate materials floated to form a mantle and primitive crust. The planet had a primordial atmosphere, likely rich in hydrogen and helium captured from the solar nebula, plus volcanic gases released from the interior. The moon-forming impact, which we will explore in greater detail later, fundamentally transformed this proto-Earth. It melted much of the planet's surface, creating a global magma ocean. It vaporized the primordial atmosphere, which was replaced over time by outgassing from the interior, and it changed Earth's rotation rate and axial tilt, setting the stage for the day-night cycle and seasonal variations that would later influence the development of life. Mars, the fourth terrestrial planet, is notably smaller than its inner neighbors, with a mass only about 11% of Earth's. This small size has long puzzled planetary scientists, as conventional models of planet formation would predict a larger body at Mars's distance from the Sun. The current leading explanation involves the gravitational influence of Jupiter. According to the Grand Tack model, which we will discuss in more detail later, Jupiter migrated inward early in the solar system's history, penetrating as far as about 1.5 astronomical units before reversing course. This migration would have scattered and depleted the population of planetesimals and embryos in the Mars-forming region, leaving insufficient material to build a large planet there. Mars, according to this view, is essentially a surviving planetary embryo, one that never had the opportunity to grow to Earth-like sizes because Jupiter disrupted its feeding zone. Mars does preserve evidence of a violent early history. Its northern hemisphere is dramatically lower in elevation than the southern hemisphere, so it feature called the crustal dichotomy. One proposed explanation is that the northern lowlands represent a giant impact basin, the Borealis Basin, formed by a collision with a body perhaps 1,600 to 2,700 kilometers in diameter. If confirmed, this would be the largest impact structure in the solar system. The formation of the terrestrial planets was complete by about 100 million years after the birth of the Sun, though bombardment by leftover planetesimals continued for several hundred million years more. By this time, the inner solar system had taken on something resembling its present architecture. 4 rocky worlds, each with its own unique character, orbiting at distances ranging from 0.39 to 1.52 astronomical units from the Sun. The terrestrial planets formed from the same general reservoir of material, the rocky and metallic dust that condensed within the frost line. Yet each ended up with distinctive properties, shaped by the specific sequence of impacts it experienced and its position within the disk. This diversity of outcomes from similar starting conditions is a reminder that the formation of planetary systems involves substantial elements of chance and circumstance. Part 6. The gas giants emerge beyond the frost line. A very different story unfolded. In the cold outer regions of the solar nebula, where water and other volatile compounds could condense as ice, planetary cores grew rapidly to sizes far exceeding anything possible in the inner system. When these cores reached a critical mass, they triggered a dramatic process of runaway gas accretion that transformed them into the giant planets Jupiter and Saturn. The enhanced availability of solid material beyond the frost line was the crucial factor enabling giant planet formation. With roughly 3 to 4 times more mass available per unit area of the disk, planetary embryos in the outer system could grow larger and faster than their counterparts in the inner system. Additionally, the presence of icy materials changed the nature of collisions between bodies. Ice is stickier than rock, and icy planetesimals could merge more readily at higher collision velocities than rocky ones could. The first giant planet core to form was likely in the vicinity of Jupiter's current orbit, at about 5 astronomical units from the Sun. This location represented a sweet spot for planet formation, far enough from the sun for ice to condense, close enough for orbital periods to be short, allowing frequent interactions between bodies, and in a region where the surface density of the disk was still relatively high. Within perhaps 1 to 3 million years of the Sun's birth, a planetary embryo in this region had grown to roughly 10 Earth masses. This is the critical core mass, the threshold at which the embryo's gravity becomes strong enough to capture gas from the surrounding nebula faster than that gas can escape. Below the critical core mass, any gas captured by the embryo settles into a thin atmosphere in hydrostatic equilibrium. The energy released by incoming gas and in falling planetesimals heats this atmosphere, causing it to expand and resist further compression. The embryo can grow, but only slowly, limited by how quickly it can radiate away the heat of accretion. At the critical mass, this equilibrium breaks down. The atmosphere becomes massive enough that its self-gravity becomes significant, and it can no longer be supported by thermal pressure alone. The atmosphere begins to contract rapidly, drawing in more gas from the surrounding disk, which releases more gravitational energy, heating the atmosphere but also increasing its mass and gravity. A runaway process ensues, in which the rate of gas accretion accelerates dramatically. During runaway gas accretion, a giant planet can grow by orders of magnitude in mass within only 100,000 to 1 million years. The planet opens a gap in the disk, clearing out the gas in its immediate vicinity, but material continues to flow into the gap from the surrounding disk, feeding the planet's continued growth. The limit to this growth is set primarily by the availability of gas in the disk and by the planet's ability to continue capturing material as it opens an ever wider gap. Jupiter ultimately captured roughly 318 Earth masses of material, making it by far the most massive planet in our solar system. Its composition is predominantly hydrogen and helium, reflecting the composition of the gas it captured from the solar nebula. But its core, the original icy embryo that triggered the runaway accretion, is thought to still exist at the planet's center, though its exact properties remain a subject of active research. The Juno spacecraft, which has been orbiting Jupiter since 2016, has provided new insights into the planet's interior structure. Juno's precision measurements of Jupiter's gravitational field suggest that the core is not a discrete, well-defined body, but rather a diffuse, diluted region where heavy elements are mixed throughout a large fraction of the planet's interior. This diluted core structure may be the result of giant impacts early in Jupiter's history that mixed core material with the surrounding envelope, or it may reflect the original formation process. Saturn followed a similar path, but with important differences. Its core also grew beyond the critical mass and triggered runaway gas accretion, but Saturn formed later than Jupiter, after more of the disk gas had been depleted. As a result, Saturn captured less gas than Jupiter, ending up with only about 95 Earth masses compared to Jupiter's 318. Saturn is also less dense than Jupiter, with a lower fraction of heavy elements, suggesting that its core mass may be somewhat smaller relative to its total mass. Both Jupiter and Saturn are classified as gas giants, a term that reflects their predominant composition of hydrogen and helium. Despite their name, these planets do not have surfaces in the conventional sense. As one descends into their atmospheres, the gas gradually transitions from an atmosphere of familiar properties to increasingly exotic forms of matter. Hydrogen, at the extreme pressures found in Jupiter's interior, becomes metallic, conducting electricity like a metal. At the very center, temperatures may reach 20,000 degrees Kelvin or more, with pressures millions of times Earth's atmospheric pressure. The formation of Jupiter had profound effects on the rest of the solar system. Its massive gravity perturbed the orbits of nearby objects, scattering some into the inner system, ejecting others entirely, and trapping still others in resonant configurations. Jupiter is thought to be largely responsible for the truncation of Mars's growth, as discussed earlier, and for the structure of the asteroid belt, which we will explore shortly. Jupiter also influenced the formation of Saturn. As the two giant planets grew, their gravitational interactions could have led to orbital migration and changes in their mutual configuration. Some models suggest that Jupiter and Saturn were initially in a different orbital resonance than they are today, with implications for the subsequent evolution of the outer solar system. The formation of the gas giants was complete within the first 5 to 10 million years of the solar system's history, before the gas disk had fully dissipated. This early formation was essential, as giant planet formation requires gas to be present in the disk. Once the disk dispersed, driven away by the young sun's ultraviolet radiation and stellar winds, no more gas giants could form. The window of opportunity was narrow, and Jupiter and Saturn formed just in time to capture their massive envelopes. Part 7. The Ice Giants and the Distant Frontier. Beyond Saturn, the story of planet formation takes yet another turn. Uranus and Neptune, the two outermost planets, belong to a different category, the ice giants. These worlds are smaller than the gas giants, with masses of about 14.5 and 17 Earth masses respectively, and their compositions differ fundamentally from their larger neighbors. Understanding their formation has proven to be one of the more challenging problems in planetary science. The term ice giant refers not to the current state of these planets, but to the materials from which they formed. Uranus and Neptune are thought to have cores composed predominantly of water, methane, and ammonia, compounds that condense as ices in the cold outer reaches of a protoplanetary disk. Unlike Jupiter and Saturn, which are about 90% hydrogen and helium by mass, Uranus and Neptune contain only about 20% hydrogen and helium. The rest is heavier material, primarily the ices and rocks that formed their original cores. The challenge in explaining the formation of Uranus and Neptune lies in the timescales involved. At their current distances from the Sun, 19.2 and 30 astronomical units, respectively, orbital periods are long, and the surface density of the protoplanetary disk was low. Traditional models of core accretion struggle to grow ice giant cores fast enough at these distances before the gas disk disperses. Numerical simulations have shown that building a 15 Earth mass core at 30 astronomical units through conventional accretion would require longer than the typical lifetime of a protoplanetary disk, which is only about 3 to 10 million years. The problem is that collisions between planetesimals are too infrequent in the outer disk, and the escape velocities from growing bodies are comparable to or exceed the relative velocities between bodies, making ejection as likely as accretion. One solution to this problem is that Uranus and Neptune did not form at their current locations. Instead, they may have formed much closer to the Sun, in the region between Saturn and the inner edge of the outer planetesimal disk, and later migrated outward to their present orbits. This idea is a key component of the Nicene model, which we will discuss in more detail later. Another possibility is pebble accretion, a mechanism that has gained increasing attention in recent years. Pebble accretion refers to the capture of centimeter-to-meter-sized particles by a growing planetary core. Unlike the capture of kilometer-scale planetesimals, which requires close gravitational encounters, pebble accretion can occur when gas drag slows particles enough that they spiral into the core's gravitational influence. Pebble accretion can be highly efficient under the right conditions, allowing cores to grow rapidly even in the outer disk. The effectiveness of pebble accretion depends on the abundance of pebble-sized particles, the properties of the gas disk, and the mass of the core. Some models suggest that the ice giant cores could have formed through pebble accretion within a few million years, fast enough to beat the dispersal of the gas disk. Regardless of the exact formation mechanism, Uranus and Neptune ended up with compositions that reflect their origin in the icy outer regions of the solar nebula. Their interiors are thought to consist of a rocky core surrounded by a thick mantle of water and other ices, topped by a relatively thin atmosphere of hydrogen and helium. The term ice is somewhat misleading, however, as the extreme pressures in these planets' interiors prevent water and other compounds from existing as ice in the familiar crystalline form. Instead, they likely exist as hot, dense fluids or even exotic supersonic states. The supersonic phase of water, predicted theoretically and recently confirmed in laboratory experiments, is a state in which oxygen atoms are locked in a crystalline lattice, while hydrogen atoms flow freely through the lattice like a liquid. This peculiar state of matter may be common in the interiors of Uranus and Neptune, and could help explain these planets' unusual magnetic fields, which are tilted at large angles relative to their rotation axes and offset from their centers. Beyond Neptune lies the Kuiper Belt, a vast ring of icy bodies extending from about 30 to 50 astronomical units from the Sun. The Kuiper Belt is populated by tens of thousands of objects, larger than 100 kilometers in diameter, and millions of smaller bodies. These objects are remnants of the outer planetesimal disk from which the giant planets formed, material that was never incorporated into a planet but was sculpted by the gravitational influence of Neptune. The largest known Kuiper Belt object is Pluto, a dwarf planet with a diameter of about 2,377 kilometers. Pluto and its large moon Charon, along with 4 smaller moons, form a fascinating system that was explored by NASA's New Horizons spacecraft in 2015. The encounter revealed a surprisingly complex world with mountains of water ice, plains of nitrogen ice, and a thin atmosphere of nitrogen, methane, and carbon monoxide. Other large Kuiper Belt objects include Eris, which is slightly smaller than Pluto, but more massive, and Makemake and Haumea, both of which are classified as dwarf planets. These bodies and their smaller companions represent primitive material from the outer solar system, relatively unaltered since the early days of the solar nebula. Studying them provides insights into the conditions and processes that prevailed in the cold outer reaches of the disk 4.6 billion years ago. Even further from the Sun lies the Oort cloud, a hypothesized spherical shell of icy bodies extending perhaps halfway to the nearest star. The Oort cloud is thought to be the source of long-period comets, icy bodies on highly elongated orbits that occasionally plunge into the inner solar system, develop spectacular tails as their ices vaporize, and then retreat back into the distant darkness. The objects in the Oort cloud likely formed much closer to the Sun in the giant planet region, and were later scattered outward by gravitational interactions with Jupiter, Saturn, Uranus, and Neptune. Once ejected to great distances, their orbits were modified by the gravitational influence of passing stars and the tidal forces of the Milky Way galaxy, randomizing their orientations and raising their perihelia to values that keep them far from the planets. Comets that originate in the Kuiper Belt or Oort cloud are particularly valuable scientifically because they preserve pristine material from the early solar system. When these objects formed, they incorporated gases, ices, and dust that condensed from the solar nebula. Locked in cold storage for billions of years, this material remains largely unaltered, providing a direct window into the composition and conditions of the primordial disk. The European Space Agency's Rosetta mission, which orbited and landed on Comet 67P/Churyumov-Gerasimenko in 2014 to 2016, provided unprecedented insights into cometary composition. Rosetta found complex, organic molecules, including the amino acid glycine, as well as phosphorus and other elements, essential for life. The spacecraft also detected heavy water with the heavier deuterium isotope, in place of ordinary hydrogen, in ratios different from Earth's oceans, providing constraints on where Earth's water originated. The outer solar system, from the ice giants to the Kuiper Belt to the distant Oort cloud, represents the cold frontier of our planetary system. These regions have preserved material from the earliest era of solar system formation, offering us glimpses of the primordial conditions from which all the planets, including our own Earth, ultimately arose. Part 8. The giant impact that made our moon. Among all the events that shaped our solar system, few are more remarkable than the giant impact that created Earth's moon. This collision, which occurred approximately 4.5 billion years ago, involved the collision of the proto-Earth with a Mars-sized body named Theia. The impact fundamentally transformed our planet, setting the stage for the Earth we know. Today, the Moon is an anomaly among the moons of the solar system. It is unusually large relative to its parent planet, with a diameter of 3,474 kilometers compared to Earth's 12,742 kilometers, a ratio of about 0.27. For comparison, the largest moons of Jupiter and Saturn are much smaller relative to their parent planets. Additionally, the Moon orbits relatively close to Earth, at an average distance of about 384,000 kilometers, and its composition bears striking similarities to Earth's mantle while being depleted in iron and volatile elements. These peculiarities led scientists to propose that the Moon formed through a dramatically different process than the moons of the outer planets, which likely coalesced from disks of material orbiting their parent planets during formation. Instead, the giant impact hypothesis suggests that the Moon formed from debris ejected during a catastrophic collision between the proto-Earth and another planetary body. The impactor in this scenario has been named Theia. after the mythological Greek Titaness, who was the mother of Selene, the goddess of the moon. Theia is thought to have had a mass roughly 10 to 15% of Earth's mass, comparable to the planet Mars. According to one model, Theia formed in Earth's orbital vicinity, possibly at one of the Lagrange points where gravitational forces balance, before being perturbed into a collision course with Earth. Recent research published in the journal Science in 2025 by Hoppe and colleagues at the Max Planck Institute for Solar System Research provides new constraints on Theia's origin. By analyzing iron isotopes in lunar samples from the Apollo missions, Earth samples, and meteorites, and combining these with previous measurements of other elements, such as chromium, molybdenum, and zirconium, the researchers concluded that Theia likely formed in the inner solar system, possibly even closer to the Sun than Earth. This finding helps explain the isotopic similarities between Earth and Moon, as both would have formed from similar source materials. The impact itself was an event of almost inconceivable violence. Theia struck the proto-Earth at a velocity of roughly 4 kilometers per second, releasing energy equivalent to billions of nuclear weapons detonating simultaneously. The collision is thought to have been oblique, with Theia striking at an angle rather than head-on, which maximized the amount of material ejected into orbit. Computer simulations of the impact, pioneered by researchers including Robin Canup at the Southwest Research Institute, have explored various scenarios for the collision. The canonical model involves a relatively slow, grazing impact that ejects material primarily from the mantles of both bodies while their metallic cores merge. This explains why the Moon has a small iron core, only about 1.5 to 2% of its mass, compared to Earth's core, which makes up about 32% of our planet's mass. However, achieving the observed angular momentum of the Earth-Moon system and the compositional similarity between Earth and Moon has proven challenging. Alternative models have been proposed, including a higher energy impact that would have homogenized the material from both bodies, and a scenario in which Theia had already lost its rocky mantle in previous collisions and struck Earth as essentially a metallic cannonball. A striking development came in 2022 when researchers led by Jacob Kigereis at NASA's Ames Research Center published high-resolution simulations suggesting that the Moon may have formed almost immediately after the impact, in a matter of hours rather than over thousands of years. In these simulations, material from the outer layers of the colliding bodies is launched directly into orbit, where it quickly coalesces into a single large body. This rapid formation model offers new explanations for some of the Moon's observed properties. Whatever the exact details of the collision, its aftermath transformed the young Earth. The impact likely vaporized a significant portion of both bodies, creating a temporary atmosphere of rock vapor. This silicate vapor atmosphere would have radiated enormous amounts of heat, eventually condensing and raining back down onto the surface. The energy of the impact, combined with the heat released as the silicate rain fell, would have created a global magma ocean covering Earth's entire surface to a depth of hundreds to thousands of kilometers. The presence of an ancient magma ocean on the Moon is well established from studies of lunar samples. The Moon's crust is dominated by a rock type called an orthosite, which is composed primarily of the mineral plagioclase feldspar. An orthosite floats on molten basalt, and would have crystallized at the top of the magma ocean, forming a primordial crust. The widespread presence of an orthosite across the Moon's surface confirms that the Moon was indeed covered by a deep magma ocean shortly after its formation. The giant impact also influenced Earth's rotation and axial tilt. Before the impact, Earth may have been rotating at a different rate and with a different orientation than it does today. The angular momentum transferred by Theia altered both of these properties. Earth's current 24-hour day and 23.4-degree axial tilt are thought to be consequences of the impact, though both have continued to evolve over the subsequent billions of years due to tidal interactions with the Moon. In 2023, scientists led by Qian Yuan and colleagues at Arizona State University and Caltech proposed a fascinating hypothesis that remnants of Theia may still be visible deep inside Earth today. The two large low shear velocity provinces, anomalous regions in Earth's lower mantle beneath Africa and the Pacific Ocean that have been known for decades from seismic studies, could potentially be composed of material from Theia's mantle that sank to the base of Earth's mantle after the impact and has remained there ever since. Computer simulations published in the journal Nature suggest that if Theia's mantle was denser than Earth's, which geochemical evidence indicates it may have been, these iron-rich fragments could have settled at the core mantle boundary rather than mixing with the surrounding material. While this hypothesis remains to be definitively proven, it offers an intriguing possibility that we may be able to study material from the moon-forming impactor without ever leaving our own planet. The moon-forming impact had profound implications for Earth's subsequent evolution. The impact may have stripped away Earth's primordial atmosphere of hydrogen and helium, setting the stage for the development of the secondary atmosphere that arose from volcanic outgassing. The creation of the Moon stabilized Earth's axial tilt, preventing the large oscillations that might otherwise occur, and that would have dramatic effects on climate. The tidal forces exerted by the Moon have influenced ocean circulation and may have played a role in the evolution of life. The giant impact that created our Moon was one of the final chapters in the accretion of the terrestrial planets. It was violent, transformative, and uniquely consequential. Without this collision, Earth would be a very different world, perhaps with a faster rotation rate, a wildly oscillating axial tilt, and no large moon to light the night sky. The Moon, a constant presence throughout human history, stands as a monument to the chaos and chance that shaped our cosmic home. Part 9. Planetary Migration and Chaos. The architecture of our solar system has not remained static since the planets first formed. Within the first billion years of its existence, the solar system underwent dramatic restructuring driven by gravitational interactions between the giant planets and the remnant disk of planetesimals. This period of instability scattered objects throughout the system, bombarded the inner planets with debris, and may have fundamentally reshaped the orbits of Uranus and Neptune. The most influential model of this early instability is known as the Nice model, named after the city in France, where its key developers first met to formulate the theory. Published in 2005 by a team including Alessandro Morbidelli, Hal Levison, Rodney Gomes, and Cleomenius Tsiganis, the Nice model proposes that the giant planets formed at a much more compact configuration than they occupy today, and later migrated to their current positions. According to the NICE model, Jupiter, Saturn, Uranus, and Neptune originally orbited between about 5.5 and 17 astronomical units from the Sun, much closer together than their present spacings. Beyond Neptune lay a massive disk of icy planetesimals, extending outward for perhaps 30 to 35 astronomical units, and containing a total mass of 20 to 50 Earth masses. This disk would later provide the raw material for the Kuiper Belt and Oort cloud. For several hundred million years, the planets slowly migrated through interactions with this planetesimal disk. Neptune, Uranus, and Saturn predominantly scattered planetesimals inward toward Jupiter, and in the process migrated outward. Jupiter, by contrast, tended to eject planetesimals from the solar system entirely, and in doing so migrated slightly inward. This differential migration gradually increased the spacing between the planets. The turning point came when Jupiter and Saturn crossed their mutual 2-to-1 mean motion resonance, meaning that Saturn's orbital period became exactly twice Jupiter's. Resonances of this type can pump up orbital eccentricities, and in this case, crossing the resonance destabilized the entire planetary system. The eccentricities of Saturn, Uranus, and Neptune increased dramatically, and the ice giants were sent onto orbits that crossed each other's paths. What followed was a period of gravitational chaos. Uranus and Neptune experienced close encounters with each other, and with Saturn scattering wildly through the outer solar system. In some versions of the NICE model, a fifth ice giant was originally present, but was ejected from the solar system during this chaotic phase. The surviving planets eventually settled into their current, more widely spaced orbits, but not before wreaking havoc on the remnant planetesimal disk. The instability scattered the planetesimal disk in all directions. Some objects were ejected from the solar system. Others were sent inward, crossing the orbits of the giant planets and eventually reaching the inner solar system. Still others were captured into resonant orbits with Neptune, where they remain today as the various populations of trans-Neptunian objects. The inward scattering of planetesimals had dramatic consequences for the inner solar system. The late heavy bombardment, a hypothesized period of intense cratering traditionally dated to roughly 4.1 to 3.8 billion years ago, is thought by many researchers to be the signature of this instability reaching the inner planets. However, the precise timing and nature of this bombardment remains an active area of scientific debate. Some researchers have proposed that the bombardment occurred much earlier, around 4.48 billion years ago, while others suggest it was more gradual rather than a discrete spike in impact rates. What seems clear from the evidence is that the inner solar system experienced elevated bombardment during its first several hundred million years, during which the surfaces of Mercury, Venus, Earth, and Mars were subjected to a barrage of impacts far more intense than anything that has occurred since. Evidence often cited for the late heavy bombardment comes primarily from the Moon. Lunar samples returned by the Apollo missions have been dated using radiometric techniques, and many of them yield ages clustered between about 3.8 and 4.0 billion years. These ages correspond to the formation of impact melt rocks, materials that were melted by the heat of large impacts and then cooled and crystallized. This clustering of ages was initially interpreted as evidence that impact rates were much higher during this specific period, though some scientists have cautioned that this pattern could partially reflect sampling bias, since the Apollo landing sites were chosen near large impact basins. The heavily cratered surfaces of the Moon and Mercury preserve a visual record of this ancient bombardment. The large circular basins that dominate these surfaces, features like the Moon's Imbrium and Oriental basins, or Mercury's Caloris basin, are believed to have formed during this period of elevated impacts. On Earth and Venus, where geological activity has erased the ancient impact record, only indirect evidence remains, such as spherular layers in ancient rocks that may represent condensed droplets from impact-generated vapor plumes. The NICE model, in its various incarnations, has been remarkably successful at explaining a wide range of features of the solar system. It accounts for the current orbital architecture of the giant planets, including their eccentricities and inclinations. It explains the structure of the Kuiper Belt, including the existence of resonant populations locked in orbits with Neptune. It provides a mechanism for the late heavy bombardment, linking it to a specific dynamical event rather than a gradual decline from primordial bombardment. And it offers explanations for the origin of Jupiter's Trojan asteroids and the irregular satellites of the giant planets. Complementing the NICE model is the Grand Attack hypothesis, which addresses an earlier phase of migration driven by interactions with the gas disk, rather than the planetesimal disk. According to the Grand Attack proposed in 2011 by Kevin Walsh and colleagues, Jupiter formed at about 3.5 astronomical units from the Sun, and then migrated inward to approximately 1.5 astronomical units before reversing course. Jupiter's reversal was caused by its capture of Saturn into a 3:2 mean motion resonance. When two planets are locked in such a resonance, the balance of torques exerted by the gas disk on the planets can reverse, turning inward migration into outward migration. Jupiter and Saturn then migrated outward together, eventually reaching roughly their current orbital distances by the time the gas disk dispersed. The Grand Attack hypothesis was developed primarily to explain the small mass of Mars. In conventional models of planet formation, the region where Mars formed should have contained enough material to produce a planet comparable in mass to Earth or Venus. Instead, Mars is only about 11% of Earth's mass, essentially a planetary embryo that never completed its growth. Jupiter's inward migration would have disrupted the inner disk, scattering planetesimals and truncating the distribution of solid material available to form Mars. After Jupiter reversed course and migrated back outward, it would have deposited some material back into the asteroid belt, but the Mars region would have remained depleted. The Grand Attack thus provides a dynamical explanation for one of the most puzzling features of the inner solar system. The combination of the Grand Attack and NICE models provides a comprehensive framework for understanding the dynamical evolution of the solar system over its first billion years. From a compact initial configuration, the giant planets migrated, interacted, and eventually reached their current orbits through a series of instabilities and resonance crossings. This migration sculpted the distribution of small bodies throughout the system and fundamentally influenced the final stages of terrestrial planet formation. The chaotic nature of these processes means that the solar system's current architecture is, in a sense, accidental. Small changes to the initial conditions, such as the precise masses or orbital parameters of the giant planets, could have led to very different outcomes. Jupiter might have continued migrating inward rather than reversing, potentially disrupting the inner solar system entirely. The late heavy bombardment might have been more intense, sterilizing the early Earth. The ice giants might have been ejected, leaving only Jupiter and Saturn in the outer system. The solar system we inhabit represents just one possible outcome among many. Its particular arrangement of planets, its asteroid belt, its Kuiper belt, and its distant Oort cloud all bear the imprint of the chaotic dynamics that unfolded in its earliest epochs. Understanding this history helps us appreciate both the cosmic contingency of our existence and the dynamic nature of planetary systems in general. Part 10. The Final Architecture. By approximately 4 billion years ago, our solar system had largely assumed the form we recognize today. The violent era of giant impacts had concluded. The planetary migrations had subsided. The period of elevated bombardment appears to have been waning. What emerged from these tumultuous first 600 million years was a system of 8 planets, countless smaller bodies, and a stable architecture that would persist largely unchanged for the next 4 billion years and counting. The inner solar system, scarred by the bombardment but no longer subject to world-shaping collisions, began a new chapter in its evolution. Mercury, Venus, Earth, and Mars settled into orbits that would remain stable for billions of years. Each planet, having accumulated its final mass, began the long process of geological evolution that would differentiate their surfaces and interiors. Mercury, the smallest planet, cooled rapidly and became geologically quiescent relatively early. Its thin crust, depleted mantle, and oversized iron core were fixed in place. Today, Mercury's surface is dominated by ancient impact craters, many believed to date from the early bombardment period, with little evidence of significant geological activity since. Venus followed a different path. Despite being nearly Earth's twin in size and mass, Venus developed a thick atmosphere dominated by carbon dioxide and experienced runaway greenhouse heating that raised surface temperatures to approximately 465 degrees Celsius. The planet's surface appears to have been catastrophically resurfaced by volcanic activity roughly 500 million years ago, erasing all evidence of its earlier geological history. Earth, uniquely among the terrestrial planets, developed an active hydrological cycle and plate tectonics that have continuously resurfaced the planet throughout its history. The oldest rocks on Earth date to about 4 billion years ago, with only a few crystals of the mineral zircon preserving evidence of still earlier times. The combination of liquid water, active geology, and the protecting influence of its magnetic field made Earth uniquely hospitable for the emergence and persistence of life. Mars, having been stunted in its growth by Jupiter's early migration, cooled and lost its ability to sustain a thick atmosphere and liquid surface water within its first billion years. Evidence suggests that Mars once had rivers, lakes, and perhaps even an ocean in its northern hemisphere, but these disappeared as the planet's internal heat waned and its atmosphere thinned. Today, Mars is a cold, dry world, its ancient river valleys and lake beds preserved as monuments to a more clement past. The asteroid belt, the debris field between Mars and Jupiter, represents material that was never allowed to coalesce into a planet. Jupiter's gravitational influence perturbed the orbits of objects in this region, increasing their relative velocities and turning collisions from constructive to destructive. The asteroids we observe today are fragments from this process, the shattered remnants of planetesimals that might otherwise have built a fifth terrestrial planet. Jupiter and Saturn, the two gas giants, continue to dominate the outer solar system with their massive gravitational influence. Together, they contain more than 90% of the planetary mass in our solar system. Their family of moons, including the four large Galilean satellites of Jupiter and Saturn's giant moon Titan, form miniature planetary systems of their own. Uranus and Neptune, the ice giants, occupy the cold outer reaches of the planetary system. Their tilted rotation axes, unusual magnetic fields, and mysterious internal heat sources continue to puzzle scientists. Both planets host families of moons and ring systems, though neither has been visited by a dedicated mission since Voyager 2 flew by in the 1980s. Future missions to these distant worlds are among the highest priorities for planetary exploration in the coming decades. Beyond Neptune, the Kuiper Belt extends as a vast ring of icy debris, the frozen remnants of the outer planetesimal disk from which Neptune formed. Pluto and its companions orbit here, along with thousands of other objects awaiting discovery and exploration. The Kuiper Belt's structure preserves information about Neptune's migration, with various populations of objects locked in resonances or scattered onto highly elliptical orbits. Further still, at distances measured in tens of thousands of astronomical units, lies the Oort cloud. This spherical shell of cometary nuclei represents the outermost boundary of the Sun's gravitational influence, material that was ejected from the giant planet region billions of years ago and captured into weakly bound orbits. Occasionally, gravitational perturbations from passing stars or the galactic tide nudge objects from the Oort cloud onto trajectories that bring them into the inner solar system, where they appear as long-period comets, the processes that shaped our solar system, from the collapse of a molecular cloud to the formation of planets, to the migrations and instabilities that established the final architecture, are not unique to our corner of the galaxy. Astronomers have now discovered more than 6,000 planets orbiting other stars, and the diversity of these systems is astonishing. Some stars host planets larger than Jupiter, orbiting closer than Mercury does to our Sun. Others have multiple planets packed into orbits smaller than Mercury's. Still others have planets on highly elliptical orbits that would be unstable in our system. This diversity suggests that the particular outcomes of planet formation depend sensitively on the initial conditions and the specific sequence of events that occur in each system. Our solar system, with its inner rocky planets, outer gas giants, and cold ice giants beyond, represents one path through the branching possibilities of planetary evolution. Other paths lead to different architectures, different compositions, different potentials for harboring life. The formation of our solar system took only about 100 million years, from the collapse of the molecular cloud to the end of the main planet-building phase, a mere eye blink in cosmic terms. Yet in that brief interval, processes of stunning complexity transformed a diffuse cloud of gas and dust into a structured system of worlds. Gravity, the weakest of the fundamental forces but relentless in its action, gathered matter together. Chemistry determined which materials could condense at different temperatures and distances from the young sun. Dynamics, the dance of orbits and collisions, shaped the final arrangement of planets. The result of all these processes is the solar system we call home, a system that includes at least one planet where the right conditions came together to allow life to emerge and evolve. That life eventually developed the ability to understand its own origins, to reconstruct the history of its cosmic neighborhood, and to wonder about the existence of life elsewhere in the universe. Tonight, we have traced an extraordinary journey from a cold cloud of gas and dust to a system of worlds orbiting a stable star. We have seen how a supernova may have triggered the collapse of our solar nebula, how the spinning disk gave rise to the sun at its center, and how particles of dust stuck together to form the building blocks of planets. We have explored the frost line that divided the rocky inner planets from the giant outer worlds, and we have witnessed the violent collisions that shaped Mercury, Earth, and our moon. We have followed the emergence of Jupiter and Saturn as they captured massive envelopes of hydrogen and helium, and we have contemplated the mysteries of Uranus and Neptune in the cold outer reaches. We have traced the migrations and instabilities that scattered the solar system's architecture, bombarding the inner planets and sculpting the asteroid and Kuiper belts. And we have arrived, finally, at the system we know today, 4.6 billion years old and remarkably stable. The story of our solar system's formation is still being written. Every meteorite that falls to Earth, every spacecraft that visits a comet or asteroid, every observation of protoplanetary disks around young stars adds new details to our understanding. Scientists continue to debate the exact timing of events, the mechanisms that drove key transitions, and the particular conditions that made our system turn out the way it did. What we can say with confidence is that our solar system is a product of universal physical processes, operating under particular circumstances. The same laws of physics that shaped our neighborhood also shape planetary systems around other stars. The same types of materials forged in the cores of dying stars and scattered across the galaxy provide the raw ingredients for worlds throughout the cosmos. Looking up at the night sky, we see not just points of light, but potential solar systems, some perhaps harboring worlds not unlike our own. The processes we have explored tonight have played out countless times across our galaxy and continue to do so. Today, new stars are being born at this moment, surrounded by disks of gas and dust, where planets are beginning their long journey from microscopic grains to worlds. The earth beneath your feet, the air you breathe, the very atoms in your body were all forged in this cosmic crucible. Every element heavier than hydrogen and helium was created in a star and dispersed into space. Every grain of matter that built our planet was once part of the solar nebula that collapsed 4.6 billion years ago. You are made of stardust, assembled by gravity and chemistry into a form capable of contemplating its own origins. If you have found this journey through cosmic history meaningful, please consider liking and subscribing to the channel. Your support helps bring more explorations of the universe's greatest mysteries to fellow travelers curious about our place in the cosmos. Until next time, remember that every planet in our solar system, every moon, every asteroid and comet began as nothing more than dust drifting in space around a newborn star. From that humble beginning arose everything we know, including the remarkable creatures who can look back across billions of years and piece together the story of how it all came to be. Sleep well tonight, knowing that you rest on a world forged in cosmic fire, shaped by ancient collisions, and stabilized through billions of years of gravitational dance. The universe created you from dust and starlight, and in return, you have created stories to make sense of the universe. That exchange between cosmos and consciousness may be the most remarkable outcome of all. Good night. Additional explorations, the evidence preserved in stone. Before we close this evening's exploration, let us spend a few more moments considering the remarkable witnesses to our solar system's birth that have survived to the present day. Meteorites, those fragments of ancient rock that fall from space to Earth's surface, are perhaps the most valuable objects in all of science for understanding planetary formation. They are time capsules, preserving materials and conditions from the very earliest epochs of our cosmic neighborhood. The most primitive class of meteorites, the chondrites, have remained essentially unchanged since they formed 4.567 billion years ago. Their name derives from chondrules, small spherical inclusions typically about 1 millimeter in diameter that are found embedded within them. These tiny spheres are frozen droplets of once molten silicate material, formed by brief but intense heating events in the solar nebula, and then quickly cooled. The exact mechanism that formed chondrules remains one of the great mysteries in planetary science, with proposed explanations ranging from shock waves in the disk to lightning strikes to planetesimal bow shocks. Within chondritic meteorites, scientists have also found calcium aluminum-rich inclusions, abbreviated as CAIs. These white, irregularly shaped objects represent the very first solids to condense from the hot, cooling solar nebula. Radiometric dating of CAIs has established the age of the solar system with remarkable precision: 4.567 billion years, with uncertainties of only a few million years. When we say the solar system is 4.6 billion years old, we are referring primarily to ages derived from these ancient inclusions. The composition of CAIs reflects the extreme temperatures at which they formed. They are composed of minerals rich in calcium, aluminum, and titanium, elements that condense at temperatures above 1,300 degrees Kelvin. In contrast, chondrules formed at somewhat lower temperatures, around 1,400 to 1,900 degrees Kelvin, depending on their composition. The presence of both CAIs and chondrules in the same meteorite indicates that the solar nebula experienced a range of thermal conditions and that materials formed at different temperatures were eventually mixed together. Pre-solar grains represent an even more ancient component found within some primitive meteorites. These microscopic particles, typically only a few micrometers in size, predate the solar system entirely. They formed in the outflows and explosions of dying stars and drifted through interstellar space until they were incorporated into the cloud that collapsed to form our solar system. Scientists identify pre-solar grains by their highly anomalous isotopic compositions, ratios of different isotopes that could not have been produced in our solar system, but are characteristic of particular types of stars, such as asymptotic giant branch stars or supernovae. The study of pre-solar grains has revealed that our solar system formed from material contributed by many different stellar sources, carbon-rich grains from asymptotic giant branch stars, silicate grains from red giants, and diamond nanoparticles possibly formed in supernovae have all been identified. This confirms that the elements from which our planets formed were synthesized in multiple generations of stars over billions of years before our sun was born. Iron meteorites represent a different window into solar system history. Unlike chondrites, which are primitive aggregations of material that never experienced significant heating, iron meteorites are differentiated materials, fragments of the metallic cores of asteroids that grew large enough to undergo melting and separation of metal from silicate. The existence of iron meteorites proves that some planetesimals in the early solar system grew to sizes of at least a few hundred kilometers in diameter, large enough for internal heating from radioactive decay to melt their interiors. The parent bodies of iron meteorites differentiated very early in solar system history, within just a few million years of CAI formation. This rapid differentiation was driven by the decay of short-lived radioactive isotopes, particularly aluminum-26, which has a half-life of only 717,000 years. When present in sufficient quantities, the heat released by aluminum-26 decay can melt the interiors of planetesimals, allowing dense metal to sink to the center and form a core, while lighter silicate material floats to form a mantle and crust. Stony iron meteorites, which contain roughly equal proportions of metal and silicate, are thought to sample the core mantle boundary regions of differentiated asteroids. Pallasites, the most visually striking of all meteorites, contain gem-quality olivine crystals suspended in a matrix of iron-nickel metal. These beautiful objects provide direct evidence of the differentiation process that separates planetary interiors into layers. Martian meteorites, though rare, represent samples of another planet delivered to Earth by chance. When large impacts strike Mars, they can eject fragments of Martian rock into space at velocities sufficient to escape the planet's gravity. Some of these fragments eventually cross Earth's orbit and fall as meteorites. The Martian origin of these rocks is confirmed by trapped gases in their interiors that match the composition of the Martian atmosphere, as measured by spacecraft. The oldest Martian meteorites record events from the first few 100 million years of Mars's history. They indicate that Mars differentiated very rapidly, forming its core and primordial crust within the first 20 to 30 million years after CAI formation. This rapid differentiation is consistent with Mars being an essentially complete planetary embryo that never experienced the giant impacts that continued to shape Earth over a longer period. Lunar meteorites provide similar insights into the Moon's history. These rocks were blasted off the lunar surface by impacts and eventually fell to Earth after orbital evolution brought them to our planet. Combined with samples returned by the Apollo missions and the Soviet Luna program, lunar meteorites have enabled detailed reconstruction of the Moon's formation and early evolution. The study of meteorites continues to yield new discoveries. Advanced analytical techniques, including nanoscale secondary ion mass spectrometry and synchrotron X-ray fluorescence, allow scientists to probe the compositions of individual microscopic grains with unprecedented precision. Each new measurement adds detail to our understanding of the conditions and processes that operated in the solar nebula 4.6 billion years ago. The ongoing story, the formation of our solar system, was not an endpoint, but a beginning. The processes of planetary evolution continue to this day, though at rates imperceptibly slow by human standards. Plate tectonics reshape Earth's surface over millions of years. Volcanic eruptions modify planetary atmospheres and surfaces. Impacts, though far less frequent than during the early solar system's period of heavy bombardment, still occur, as demonstrated by the 2013 Chelyabinsk event in Russia and the ongoing discovery of potentially hazardous asteroids. The Sun itself is evolving. Over the past 4.6 billion years, it has gradually increased in luminosity by about 30% as hydrogen in its core has been converted to helium. This slow brightening has implications for the long-term habitability of Earth and will eventually transform our planet's climate. In approximately 1 billion years, the Sun's increasing luminosity is expected to trigger a runaway greenhouse effect on Earth, ending our planet's era as a habitable world. Further in the future, perhaps 5 billion years from now, the Sun will exhaust the hydrogen fuel in its core and begin its death throes. It will swell into a red giant, potentially engulfing Mercury and Venus, and scorching Earth into a molten wasteland. Eventually, the Sun will shed its outer layers as a planetary nebula and contract into a white dwarf, a dense stellar remnant that will cool gradually over trillions of years. The fate of the outer solar system will be determined by these changes in the Sun. As the red giant Sun loses mass through stellar winds, the orbits of the surviving planets will expand outward. Jupiter, Saturn, Uranus, and Neptune will likely survive the Sun's red giant phase, though their moons and ring systems will be altered by the changing radiation environment. On even longer timescales, the solar system will eventually be affected by close encounters with other stars. The Milky Way galaxy contains hundreds of billions of stars, all orbiting the galactic center. Over millions and billions of years, our solar system will pass close to many other stars, and their gravitational influence will gradually perturb the orbits of the outer planets and the objects in the Kuiper Belt and Oort cloud. Eventually, perhaps in tens or hundreds of billions of years, all the planets may be stripped away, and the Sun, by then a cold white dwarf, will wander through the galaxy alone. These timescales are so vast as to be almost meaningless in human terms. Yet they remind us that the solar system we observe today is a snapshot of an ongoing process, a moment frozen in the vast flow of cosmic time. The planets we know, the comets and asteroids that share our neighborhood, even the Sun that warms our world, are all temporary configurations in a universe where change is the only constant. What has remained constant throughout all these changes is the fundamental physics that governs the behavior of matter and energy. The laws of gravity that caused the solar nebula to collapse 4.6 billion years ago are the same laws that keep the planets in their orbits today and will eventually govern their fates in the far future. The processes of chemistry that determined which minerals could condense at different temperatures in the protoplanetary disk are the same processes that operate in the atmospheres and interiors of planets today. The cycles of stellar birth and death that enrich the galaxy with heavy elements continue to operate, creating new raw materials for future planetary systems. Throughout the galaxy and throughout the universe, the same processes that built our solar system are at work right now. New stars are forming in molecular clouds, surrounded by disks of gas and dust, where planets are coalescing. Somewhere at this very moment, a supernova is exploding, scattering the products of stellar nucleosynthesis into space, and perhaps triggering the collapse of a nearby cloud. Planets are being born, growing through accretion, experiencing their own giant impacts and migrations. The story of planetary formation is not just our story, it is a universal story, written in the physics of the cosmos. Scientists estimate that there are more planets in the Milky Way galaxy than there are stars, perhaps hundreds of billions of worlds in our galaxy alone. Each one of these planets has its own history, its own formation story, its own unique combination of circumstances that brought it into being. Some orbit close to their stars in blistering heat. Others drift through the cold, outer reaches of their systems. Some may be rocky worlds with liquid water on their surfaces. Others may be gas giants with crushing atmospheres and no solid ground. The diversity of planets is a testament to the creativity of physical law, the many ways that the same basic processes can unfold under different conditions. Among all these countless worlds, we know of only one that has given rise to life, our own. This may be because life is genuinely rare, requiring conditions so specific that they occur on only a tiny fraction of planets. Or it may be because life is common but difficult to detect across the vast distances between stars. We do not yet know which of these possibilities is correct. What we do know is that the processes that formed our solar system and our planet created the conditions under which life could emerge and flourish. In that sense, understanding planetary formation is essential to understanding our own origins. The atoms in your body were forged in the cores of ancient stars, scattered across space by supernova explosions gathered into the solar nebula 4.6 billion years ago, incorporated into the disk of material around the young sun, accreted into planetesimals, and then into the growing Earth, and eventually cycled through the biosphere to become part of you. You are literally made of star stuff, assembled by the same processes we have discussed tonight into a form capable of contemplating its own origins. This is perhaps the most remarkable outcome of all. That matter, organized by the blind operations of physical law over billions of years, can become aware of itself and seek to understand how it came to be. As you drift off to sleep tonight, consider that you are lying on a fragment of the solar nebula, breathing gases exhaled by ancient volcanoes, warmed by the same nuclear fires that lit up the sky over the newly forming planets 4.6 billion years ago. The ground beneath you was once dust floating in space. The water in your cells may have been delivered by comets from the outer solar system. The iron in your blood was forged in the core of a massive star that died before our sun was born. We are all children of the cosmos, products of processes that began long before Earth existed and that continue far beyond the boundaries of our little world. Understanding these processes helps us appreciate both the contingency and the inevitability of our existence. It was contingent on a particular sequence of events, a particular arrangement of matter and energy, a particular history of collisions and migrations and chemical reactions. Yet it was also inevitable that some such process would occur somewhere. That matter would organize itself into stars and planets, and eventually into beings who could ask how it all began. The universe is vast beyond comprehension, filled with wonders that we are only beginning to discover. The formation of our solar system is one small chapter in a story that spans 13.8 billion years and encompasses everything that exists. Yet it is the chapter that matters most to us, for it is the chapter in which we appear. Understanding our origins is the first step toward understanding our place in the cosmos and our responsibilities to the fragile world that we have inherited. Thank you for joining me on this journey through billions of years of cosmic history. May your dreams tonight be filled with visions of spinning nebulae, growing planets, and the countless worlds that await our discovery. Until our paths cross again among the stars, good night.